So intermolecular forces are what holds condensed states, that's liquids and solids, together. The strength of those forces depends on the structure of the particles. And this is one of the reasons we've talked about molecular shape and polarity before we get to this, because we need that to understand how the intermolecular forces work. So at a given temperature, the state of matter depends on the strength of the intermolecular forces. If you have strong forces, you could think of this as stick-togetherness, how sticky the particles are, how attracted they are to each other. If those forces are strong, then it's going to take a lot more thermal energy in order to partially break them to melt or completely break them to go into a gas state. So strong forces, we're going to have high melting and boiling points. If those forces are weak, it doesn't take much energy for them to break free, and we'll have low melting and boiling points. These forces arise from interactions between charges. Some of those charges are permanent, some of them are temporary, some of them are full charges, like a +1 and a -1 being attracted like ions, but a lot of them are partial charges, like in polar molecules. But it all has to do with electrical charges. So here's Coulomb's law again. We really don't need this 1/pi business, but that's the constant. The potential energy of two oppositely charged particles depends on the magnitude of their charges and on the distance between them. So this energy will be negative, meaning they are attracted. The energy becomes lower when these charges are opposite in sign. So that's attraction. If R is a small number, then this will be a larger negative number, more attraction. If R is large, then the force of attraction is less. And you can demonstrate this at home with a refrigerator and a magnet and a few pieces of paper. Stick one paper on the fridge with a magnet. Sticks up just fine. Put another piece of paper up there. Keep adding paper. Adding paper increases the distance between the surface of the refrigerator and the magnet, right? And at some point, depending on how strong your magnet is and how thick your pieces of paper are, at some point the magnet and the papers will start to slide down. And if you keep going, you can't even get it to stick anymore because the distance between them has gotten too large, right? And so when we think about these intermolecular forces, the strength of them depends on the charges involved. How big are the charges? Are they actual ions or are they polar molecules? And it also depends on the distance between them. Any questions? So bonding forces involve large charges at very close distances. So here within this water molecule, we have a covalent bond between this oxygen atom and the hydrogen atom. The distance between those two atoms is 96 picometers. So we have a very, very small distance, and this force here is a covalent bond, and it's going to be significantly strong. Intermolecular forces are not covalent bonds. They are forces of attraction between molecules. And so this force is going to have a long distance between it because these particles just can't get super close together. And so we might have a distance here of like 300 picometers. So this attraction between the two water molecules is going to be weaker because the distance is larger. That makes sense? Like the magnets, you've got a whole bunch of pieces of paper there. It's not going to stick as tightly as if you had no paper at all. So what are these forces? There's 4 of them we're going to talk about. The first one is the dispersion force. This also has a couple of other names, which I'm just going to tell you about because you might hear about them. It's sometimes called induced dipoles, induced dipole force. That's my favorite name because I think it's more descriptive. Sometimes called van der Waals forces or London forces. or London dispersion forces, or, I mean, there's just all kinds of different names. This is an intermolecular force that's present in all molecules and atoms. Everything has dispersion forces. And this is a result of fluctuations in the electron distribution within the molecules or atoms. So here, just looking at, what element is this, do you think? Helium, right? 2 electrons. So here we have helium, and remember, those electrons occupy an orbital, but if we tried to take a picture of them, we would force them to be particles, right? And so if we took a picture, we might see that, oh, they're here and here, and another time they're over here, and this time when we force them into being a particle, they're both over here on this side, right? So the distribution of them can fluctuate. If they're both over here, then this atom is lopsided, right? All the negative charges are on one side. This side of the atom is going to be slightly negative. So we use that lowercase Greek delta. And this side is going to be slightly positive because essentially this nucleus is exposed. So it's not an ion, we haven't lost the electrons, but the electrons happen to, in this instant, both be on one side. Okay? This is called an instantaneous dipole. It's an imbalance of charge. An instantaneous dipole An instantaneous dipole in one helium atom can induce a dipole in a neighboring helium atom. Because if this one's lopsided and there's this exposed nucleus here, that's going to attract the electrons in a neighboring atom and cause this one to get lopsided as well. And now we have this force of attraction, the dispersion force between this temporary partial charge and this temporary partial charge. Yes? Well, this was lopsided, but it's only going to be lopsided for an instant. And then it's going to go back because the electrons are just all over the place, right? And I sometimes talk about, well, that sentence didn't go very well. I talk about my kids a lot. Let's pretend this is the house. I'll make this a better color, orange. And we're just monitoring, where's Andrew? He's the little one, he's the 9-year-old. And so if you just looked at any given time, okay, there's Andrew, here's Andrew, there's Andrew, here's Andrew, here. So, you know, there's the bathroom, not in the shower because that's no good, but over here where the TV and the computer are. And then sometimes he's over here, okay? Literally, when he was 2 years old, he took the big wheel from the neighbor's yard across the street and went 3 blocks to his uncle's house, just by himself. It was like, man, the house is quiet. Where is that little booger? Well, that involved doing, increasingly large circles driving around the neighborhood, and it was a little bit scary, but he always comes back. But he's unpredictable like electrons are, right? And so, yes, this is the orbital, and we expect the electrons to be in that, but that's really just a region of probability, right? Like, okay, 90% of the time, electrons are within the orbital. And we're not even really saying what are they doing within the orbital. Do they have to be evenly distributed all the time? No, they don't. They can get lopsided. Okay? So this gets lopsided, just kind of like this diagram's a little lopsided because, he's over there a lot more than he is other places. He used to spend a lot of time up here because he always came and slept with us. Just showed up in the middle of the night and you'd wake up in the morning and, oh, there he is, little space heater. He doesn't do that anymore, thank goodness. So this is just one kid doing this. You put some more kids in there, some more electrons in there, and you can see how things could get lopsided. I kid you not, one day I walked into the living room, and all 6 of them were on half of the couch. They were looking at something. I don't know what it was. I took a picture because that's never happened again. Just spontaneously, all 6 of them on the couch, right? That can happen, just spontaneously, some electrons in this atom, just for random reasons, all on one side, right? So that's an instantaneous dipole. It doesn't last very long. They didn't stay on the couch together because ew. And then it goes away. But in that instant, it can induce a dipole in a neighboring atom. So I also think of this as being like people on one of those blue and white cruises around the San Francisco Bay. You know, they get a whole bunch of people on this boat and drive them out and around Alcatraz and stuff, right? Hopefully the boat's not overloaded, but you know, some of those places seem a little shady. So you can imagine you get this boat, right? And it's like Labor Day weekend or something, so there's lots and lots of people. It's just loaded. And so the boat goes out, it's driving around, and then we see Alcatraz. And everybody's attracted. They want to see Alcatraz, right? So they're not going to stay on this side of the boat. They're going to go over here because they're attracted to what's over here. So if everybody goes to one side of the boat, what's that going to do to the boat? It's going to list, maybe, just a smidge, right? It's not going to tip over, but it's just going to get a little bit wonky, right? And so if that's noticeable enough, that might cause the people in another boat to look at this boat because they're like, ooh, are they going to tip over? Get the idea? And then it goes away. So there's this very minor attraction, and it only lasts a very brief moment in time. But it happens over and over and over and over again. Okay? A little bit happening frequently adds up. It's like a dripping faucet. I mean, you put a bucket under it, and it's just, one drip every 15 seconds or something. But after a while, the bucket's full, right? It adds up. Oops. Did I skip something? No, I didn't. Okay. So the strength of this, the magnitude of the dispersion forces, depends on how easily the electrons can move around, can be polarized, can get lopsided. If you have a large molecule, a large atom, I think of them as being big and flabby, right? And so it's easier for these electrons to get lopsided. The electrons are held less tightly to the nucleus. The ones on the outside certainly are much farther from the nucleus, and so they're more able to jiggle around and get lopsided. So we see that as atomic size increases, that the strength of the dispersion force increases. And we can see that change by looking at the boiling point. So these are noble gases. As we go down a period, they increase in size. We can look at the boiling point. That's in Kelvin, so 4.2 Kelvin is really, really small. 165 Kelvin is still way, way below zero. But that temperature is significantly higher than 4.2, which says that this xenon atom has a lot more dispersion forces than helium. So this comparison is very nice because we're comparing very similar things, noble gas atoms. But in general, dispersion force will increase with the molar mass. So the larger the molecule or the atom is, in general, the larger the dispersion force. Any questions? If you look at the periodic table, are the gases mostly the smaller atoms or the larger atoms? They're more the smaller ones. They're the ones at the top of the periodic table, right? Of course, the noble gases want to be exceptions to everything. And we'll see why all of them are gases. The shape of a molecule also plays a part in the strength of dispersion forces. Here we have N-pentane and neopentane. And so these two molecules have exactly the same molar mass because they have the same number of carbon and hydrogen atoms. They're just connected differently. Neopentane has more of a ball shape, and N-pentane is more linear. And so we can think in terms of this as the intermolecular force of dispersion forces as being a little bit like Velcro. So here we have these two molecules, and they can have more surface area in contact or close proximity with each other. So if you imagine these covered in Velcro, these are probably going to stick together pretty well. If you have two spheres, they can only touch at one point, a very small area, and so they can't stick together as easily. So we predict that this is going to have a lower melting point, a lower boiling point than this one, even though they have the same molar mass, just because the surface area contact here is going to be much less than with this shaped molecule. So we have to consider shape in addition to molar mass. And so we're careful in what sorts of comparisons we ask you to make, because we can't just compare random things. We have to be careful in what we choose to compare. So here is a comparison of they're called normal hexanes, meaning there's no branching in their chains. They're all just normal pentane, 5 carbons in a line with hydrogens around, 6 carbons, 7, 8, 9. But we see the molar mass is increasing. We see the boiling point is increasing. The boiling point is increasing for 2 reasons. One, increased polarizability because the molecules are larger, but we've also got greater surface area with the longer molecules. This would be, like long sheets of Velcro versus just a little piece, right? So I don't know if any of you, I don't think people your age still have Velcro shoes, but do you remember when you were a kid and you had Velcro shoes? And you're like, this little Velcro tab just will not stay put, right? But then you go to a carnival and they have one of those cool bounce houses where you put on this Velcro suit and you jump on the wall, right? And you stick. It's like, it can hold my body up here, but it can't keep my shoe fastened. Well, there's a big difference, isn't there? When you've got that suit on, you've got huge surface area between you and that Velcro wall. Whereas your shoe is just this little tiny square, right? And so it's not going to hold as well. So that's one force. The next one is called a dipole-dipole force. And this is an interaction between 2 dipoles. This exists in all molecules that are polar. Okay, we learned how to predict whether a molecule is polar or not. This force is stronger than the dispersion force because these are permanent dipoles. That charge is always there. It's not coming and going. So here we've got a space-filling model, and this is a polar molecule. We've got an oxygen here, and these are carbons and hydrogens. So this end of the molecule is always a little bit negative. This end is always a little bit positive. So the negative end of one molecule is going to be attracted to the positive end of the neighboring molecule. And that's the dipole-dipole force. You can look at the electrostatic potential map, looking at the electron density, and we see that there's more electrons over here and fewer over here. And so it's the attraction between partial charges. Any questions? So polar molecules have dipole-dipole forces in addition to dispersion forces. All things have dispersion forces. All polar molecules also have dipole-dipole forces. So if we look at 2 molecules with a similar molar mass, we want to keep the molar mass similar because larger molar mass, we'd have a longer or larger dispersion force, and we want to just look at the strength of the dipole-dipole force. So here we have formaldehyde and ethane, very similar molar masses. Here are their Lewis, well, kind of Lewis structures, not showing any of the lone pairs. But if we look at this, we should be able to predict that this is going to be polar because all of the atoms bonded to the carbon are not the same, right? We've got an oxygen, which is quite electronegative, and then we've got these carbon-hydrogen bonds that are nonpolar. So this is going to be a polar molecule. Here we've got all carbon-hydrogen bonds. And I told you that's the one bond between different elements that I want you to remember is a nonpolar bond. If all the bonds are nonpolar, the molecule is nonpolar. So we can compare boiling point and melting point. So this boils at minus 19.5 degrees Celsius. This boils at minus 88. This higher boiling point, the melting point is also higher, is because of the dipole-dipole force that is also present in addition to the dispersion force. That make sense? We talked a little bit about dipole moments, and they're measured, one common unit is a debye. So we don't really need to know what a debye is, but this is increasing dipole moment, which means increasing separation of charge. So the partial charge on this molecule is larger than the partial charge on this molecule. So we see as we increase the dipole moment, the degree of polarity, we see that the boiling point increases. These all have similar molar masses, so it's not that the dispersion forces are stronger, it's just that the increased dipole moment is causing them to stick together more. So when we talk about liquids mixing together, the word we use is miscibility, the ability to mix without separating. That's a weird word. It sounds like mixability, and it means essentially the same thing, so if that helps. Miscibility is mixability of two liquids being able to mix without separating. Here we have an illustration of two clear, colorless liquids, and you pour them into this beaker, and the one sits on top and the other's on the bottom. And you could stir this or shake this or do whatever you want, but just like oil and vinegar in a salad dressing, as soon as you stop agitating it, they're going to separate. So what we've got up here is pentane, and this is water. Pentane only has carbons and hydrogens. It's nonpolar, doesn't have any polar bonds. This is nonpolar, this is polar. Water has dipole-dipole force attractions. So the water molecules are attracted to each other more strongly than the pentane molecules are attracted to each other or to the water. And so the water is like really tight on itself, and so it just excludes the pentane. The pentane's floating because it's less dense, but it's excluded because of the difference in polarity. So like dissolves like is a little saying that helps us to predict, are these things going to be miscible or not? If they're both polar, they will probably mix. If they're both nonpolar, they will probably mix. But if one's polar and one's nonpolar, probably not, because they are not alike. Okay, so that's what like dissolves like means. So let's see what we've learned. Which of these molecules have dipole-dipole forces? What do you need to know before you can answer that question? Yeah, we need to know if the molecules are polar or not. How do we do that? Lewis structures. Dang, there it comes again. Okay, so this is Ci4, and I wrote the name here just so that you don't think it's Cl4. It's carbon tetraiodide. So I'll spare you the long, involved discussion of how I come about this Lewis structure. Oh, that's going to be too big now. But it would look like this. So these bonds are polar, right? Carbon and iodine are different. It's not carbon-hydrogen, so we predict that those are polar bonds. Is the molecule polar then? Remember my trick for that? Instead of thinking about adding vectors, we're going to ask ourselves two questions. Are there lone pairs in the central atom? No, there are no lone pairs on the central atom, so first condition is met. Are all the atoms bonded to the central atom the same? Yes. Both conditions are true. No lone pairs, all atoms the same. So what does that mean? Nonpolar. Nonpolar molecules are symmetrical. So this is nonpolar. Does it have dipole-dipole forces? No. So it's a no on this one. How about CH3Cl? So CHHCl. There are no lone pairs in the central atom. Are all the atoms bonded to the central atom the same? No. So this molecule is polar. Yeah. So it's a polar molecule. Does it have dipole-dipole forces? Yes. All polar molecules have dipole-dipole forces. What about HCl? So there we have a diatomic molecule. It's only two atoms. There's only one bond. If that bond is polar, the molecule is polar. Is that bond polar? Yeah. Yeah. Because those are different. So if it was H2 or Cl2, it would be nonpolar. But we've got two different atoms there. This is polar. And therefore, yes or no? Yes. Any questions? Third type of intermolecular force. This is known as hydrogen bonding, which introduces some confusion. Hydrogen bonding is not a covalent bond, okay? And it's not bonds between hydrogens. So what is hydrogen bonding? I think of it as super dipole-dipole force, right? It is a dipole-dipole force, a force between two polar molecules, but only between there's a particular molecules that have extra high dipole moments. So you can kind of guess that hydrogen is involved, but the other criteria is that we've got fluorine, oxygen, or nitrogen bonded to the hydrogen. So hydrogen is a very small molecule, and it's not very electronegative. Fluorine, oxygen, and nitrogen are the three most electronegative elements, and they are also quite small. So if we have hydrogen bonded to one of these very electronegative yet small atoms, we're going to get high dipole moment, so larger partial charges. And because these are small, they can approach each other and get closer together. So you've got Q1 and Q2 being bigger, and you've got R being smaller. And so the force of attraction here is extra large. So how do we remember this? Yes. You were in my 3A class this summer. Remember the movie E.T.? What did E.T. do? He pointed the sky, phone home, right? E.T. phone home. Phone home. F-O-N, one of those bonded to hydrogen. That's what you need for hydrogen bonding. So here we have an illustration of, I think this is an HF molecule, so hydrogen-fluorine bond. So these partial charges are larger, closer to a full charge than in another sort of bond, maybe, phosphorus hydrogen or something. And so the force of attraction here is greater because the partial charges are larger. So the hydrogen bond is just that dipole-dipole force of attraction between a hydrogen on one atom and one of these guys on the neighboring atom. But you have to have hydrogen bonded directly to one of these. It's not just enough that you have it in the molecule somewhere. So let's look at hydrogen bonding in ethanol and in water. So here we have an ethanol molecule. We've got oxygen bonded to hydrogen. So phone home, we've got the OH going on. We just need one of them. So this bond here is especially polar. The dipole moment is larger here. So this hydrogen is going to be attracted to the oxygen on a neighboring molecule. The bond between hydrogen and oxygen is not the hydrogen bond. That is a bond between hydrogen and oxygen, but it's not the intermolecular force that we call hydrogen bonding. Hydrogen bonding is an electrostatic attraction between hydrogen on one molecule and fluorine, oxygen, or nitrogen on a neighboring molecule. Water has hydrogen bonding. So we've got the hydrogen-oxygen bond, and that's especially polar. And so this hydrogen is going to have a larger partial charge than most other polar molecules, and then oxygen's going to have a larger negative charge. And these are small, and so they're able to get close together. So it's the force of attraction between partial positive on one and partial negative on the other that's the hydrogen bond. Hydrogen bonding is very important. All of the intermolecular forces, it's important for us to know what they are. This is something that we'll carry over into OChem because it explains so many things. It's important in biochemistry and biology and all sorts of things. So just emphasizing that hydrogen bonds are between molecules, whereas chemical bonds are between atoms within a molecule. The hydrogen bonds are only like 2 to 5% as strong as a covalent bond. So they're very weak compared to covalent bonds. But hydrogen bonds are the strongest of the intermolecular forces. So if we look at, here we have two different polar molecules. Here we have an oxygen in the middle, and it's got two lone pairs on it, so we would predict that this is polar, and it is. And here we have ethanol, and that's also polar. They have the same molar mass, because the only difference is how the atoms are connected. So the same molar mass tells us that the dispersion force is going to be similar for both of these. So this difference in boiling point then has to do with, oh, it's big, huh? Ethanol has a boiling point of 78 degrees Celsius, and dimethyl ether minus 22. That's a big difference. And that big difference is due to ethanol having hydrogen bonding. Dimethyl ether has dipole-dipole forces and dispersion forces, but ethanol has all three. So it sticks together much more tightly, and so we need to get to a higher temperature. We need to get it a lot more agitated before it can break free from those bonds, because it's tighter. Water is just such a common substance. We use it all the time. We drink it, we bathe in it, we play in it. It's, all kinds of stuff that we don't really think about how crazy water is. Water is very, very weird compared to other chemicals. Here we have a graph of boiling point versus molar mass, and we're going to look at the group 6A compounds with hydrogen and the group 4A, but those are backwards. This is group 4. So really, people, and group 6 is up there. So we see a pretty nice trend here, right? I mean, this looks almost like a nice straight line, and this was a little weird dipping down there, but why is it increasing as we go to increasing molar mass? Well, dispersion forces are larger for one thing, right? So the dispersion forces getting larger would cause the boiling point to increase. These molecules here, in group 4 elements tend to form 4 bonds, and so these are pretty much going to be symmetrical, and so they're not going to have dipole-dipole forces. These are asymmetrical. They're polar molecules because each of these is going to have 2 lone pairs on the central atom, and so we see that these boiling points are higher because they're polar molecules. But then there's water, right? Way up there. You know, if we drew a line, and to predict the boiling point of water, we'd predict it to be down here somewhere, well below zero, right? For water boiling. But it's actually plus 100 instead of being maybe minus 75. Why? Hydrogen bonding. Hydrogen bonding in this small molecule gives it a much higher boiling point than it would if it was something else. So, you know, imagine what our planet would be like if water boiled at minus 75 degrees Celsius. It would not be the same, would it? All the oceans would be gone, would be gases. Our bodies, that's just not going to, we don't want to think about that. Okay, so water's very strange. And it's the hydrogen bonding that makes it do that. Between water molecules, yeah. The water molecules are so attracted to each other that they will remain a liquid at room temperature, where other substances of similar or even larger size are going to be a gas.
So it's
Strong intermolecular force gives us high melting point, high boiling point, because they stick together. So we could see questions like this on not the exam next week, but the one after. Which of these has the higher boiling point, HF or HCl? And the dreaded question, why? Well, how do we even approach this? We've got HF and we've got HCl. So we want to compare what kinds of intermolecular forces they have, and we might have to compare how strong they are. So what kind of forces does HF have? It's got dipole-dipole forces and hydrogen bonding. Does it have dispersion forces? Yeah, everything does. Dispersion. Okay, what about HCl? Does it have dispersion forces? Yeah, everything does. Is it polar? Yeah, we've got a bond here in two different elements. We're going to predict it's polar. So that means it has dipole-dipole forces. Does it have hydrogen bonding? No. It's got hydrogen in it. It's got hydrogen bonded to chlorine. But ET phone home. Fluorine, oxygen, or nitrogen bonded to the hydrogen? No, it doesn't. So this is the strongest intermolecular force. This one doesn't have that force. And so we would predict that this, being stickier to itself, would have a higher boiling point. Okay? So this has got the higher boiling point because it has stronger intermolecular forces. That make sense? How would we evaluate a question like this if maybe this one didn't have hydrogen bonding and they both just had dispersion and dipole-dipole forces? Then we would look at molar mass, or perhaps the shape of the molecule. Now these are both just diatomic molecules, so shape's not going to have much impact. But if we're just looking at dispersion forces, HCl should have stronger dispersion forces than HF because chlorine's bigger, right? Big and floppy, and well, it's kind of like the big family, small family at the fair, right? I mean, whose kids are held less tightly, right? You can't hold on to 6 kids at the same time. It's not possible. Yeah. Electronegativity does have something to do with this. Yeah. So if you were comparing, if we take hydrogen bonding out of the mix here, dispersion forces would predict that this is stronger dispersion forces, but the dipole-dipole force would be stronger with the HF because the difference in electronegativity is greater. So then, based on dipole-dipole forces, we say this has a higher dispersion forces, say that, and so then it gets a little backwards, right? But we can do this one because HF has hydrogen bonding. So we will be asking, I will, who's we? I don't know who the we is. I will be asking you questions where you have to compare melting points, boiling points, etc. And they should come down to one thing that's different, and you're looking at that different thing. So it could be difference in molar mass, so that would tell you which dispersion force is stronger. It could be differences in electronegativity. Presence or absence of hydrogen bonding is the biggest thing. The fourth force, which the book treats as an intermolecular force, is the ion dipole force. This is a force, but I disagree with calling it an intermolecular force because it's between an ion and a molecule. So that's not intermolecular. Whatever. Ion dipole, guess what? It's between an ion and a dipole. So this is when we've got an ionic compound mixed with a polar compound. So this happens when we dissolve table salt in water. Here we've got the chloride ion, and that is attracted to the positive end of the polar molecule of water. So water has a dipole, and we've got this attraction here. Sodium has a positive charge, and so it will be attracted to the negative end of the water molecule. This is also an ion dipole force. So this is very important when we're talking about aqueous solutions of ionic or polar compounds. Well, not polar compounds, just ionic compounds. This is stronger than hydrogen bonding. And this is the reason that ionic substances will dissolve in water. This is a nice summary of the different types of intermolecular forces. You should know their names, what sorts of compounds they're present in. You should understand that it's a force of attraction between opposite charges, between things, not within things. Relative strength, dispersion is weakest, then dipole-dipole, then hydrogen bonding, then ion dipole. It is important to understand, as we see this little asterisk down here, the dispersion force can become very strong, as strong and even stronger than the others for molecules of high molar mass. So like I said earlier, we have to be careful what sort of comparisons we make. I have to go with other things being equal. Okay, here's an example of the importance of hydrogen bonding. I think you all know that humans have DNA, and the DNA determines your hair color and all sorts of other different things. DNA depends on hydrogen bonding. So DNA is composed of two strands. They have a sugar phosphate backbone, and then they have these, they're called bases, thymine, adenine, cytosine, and guanine, that hang off of them almost like charms on a charm bracelet. When your body replicates the DNA, it unwinds the two strands and makes a new strand that matches each. This strand, the double strand, is held together because adenine and thymine together can form two hydrogen bonds. Cytosine and guanine can match up and form three hydrogen bonds. So these guys fit together real nicely, and those guys fit together real nicely. Now, could you have thymine forming a bond with guanine? Yes, but it would not be as strong. And so thymine and guanine never pair up. And so we have these are called base pairs. So we see that A is always with T and C is always with G. So one of the strands is sort of the opposite of the other strand. When you separate them, a new strand can be made by bringing in the right bases, and then they get linked together. And how that happens is really quite fascinating. I'm not a fan of biology. It needs to exist, but I don't need to study it. But biochemistry is fascinating. That's just absolutely fascinating. Any questions? Proteins are held together by intermolecular forces. They coil up and have their function because of the intermolecular forces. Your hair being curly or straight has to do with intermolecular forces. You can get a permanent and make your straight hair curly, and that's done by breaking those intermolecular forces, making the hair into the shape of a curl, and then reforming the intermolecular forces. I mean, it's everywhere.